Thanks very much, Jenny. I guess the first thing to say here is we'd like to thank US CLIVAR and International CLIVAR for both hosting a great meeting in Tallahassee and then following up with this Variations and Exchanges special issue. It's a great opportunity to talk about a kind of classic problem in oceanography and climate science broadly of how mesoscale eddies get their energy, where it goes, what the mechanisms for withdrawing that energy are, and what the impacts in terms of parameterizations and climate change aspects of eddy impacts on the world broadly. We have a lot of nice talks that are going to span, I think, the whole of the topics that were discussed at the meeting. And I think the last piece that I'd like to say is that simultaneously with the meeting, we found out that there is a new climate process team that's been funded that aligns with this topic very nicely. So this will not be the last of this kind of meeting we'll be seeing over the next 5 years or so. So I think that's it for me. Simon, would you like to add a little bit more?
Yeah, thanks, Baylor, and I echo your thanks to US CLIVAR and to International CLIVAR Project Office, and also just add thanks to Eric Chassignet, who hosted a very nice meeting in Florida State University. And I think at that point we can hand over to Laura and get started with the presentations. Thank you.
Okay. All right, so thank you very much, everybody, and I'll echo again the thanks to US CLIVAR and International CLIVAR for a great meeting last year. And I'm going to present some work based on the article that we co-wrote with Scott Bachman and Malte Jensen, but also kind of, encapsulate a lot of the ideas that came together when we put the Ocean Transport and Eddy Energy Climate Process team together, which is now, as mentioned by Baylor, generously funded by NSF and NOAA. So when we wrote the article, and also based on the talks that we presented last year in Tallahassee, we tried to take a pretty broad perspective on recent advances in eddy parameterization and energetics, and also trying to think about what was next, and in particular in the context of the CPT. So I'll draw on a few examples that we really tried to bring together in the article, but since I was the first presenter, I thought I'll indulge myself a couple of extra slides of introduction, which I hope will be useful for the rest of the presenters coming after me. So, the whole meeting was about the energy cycle and how mesoscale eddies fit into that broad perspective of the energy cycle. So we know they're important. So we know that energy and sources and sinks of energy and their transfer are important in maintaining the circulation and the transport. So in this little diagram on the right, we're basically forcing the ocean and the scale with wind and buoyancy at a very large scale. And then we're kind of moving towards the left where the large scale flow becomes unstable and break into smaller pieces from mesoscale eddies all the way down to turbulence. So basically kind of ranging scale of 10 to 100 kilometers all the way to basically millimeter scale. And those kind of processes move around the energy and help momentum and pressure around the ocean being transported and buried at different depths. So now it's not enough to just being moved around across scale. We also have two different types of reservoir. One is the available potential energy reservoir, and the other one is kinetic energy. And there is a lot of exchange between those two reservoirs as well. So when we try to encapsulate the energy cycle, we need to think about transfer across scale, but also transfer across reservoirs. So one key aspect that we found both in idealized model and global models is that the lack of energy transfer between scale or reservoir can have a pretty big impact on transport. So here it's just showing velocities in three different simulation. Well, actually the same model at three different resolution. 1 degree on the left, 1/4 of a degree in the middle, and on the right, 1/12 of a degree. And we're looking at the velocity as a function of depth across the Kuroshio. And what you can see is not that just the transport is faster, but also the vertical structure of the transport is quite different. And we could basically analyze how the energy transfer across scale and reservoir led to this kind of differences in the vertical structure of the flow. So the wrong energy cycle in the model can have pretty large impact both on the lateral and the vertical transport in our simulations. So now coming back to the eddies. So the eddies and mesoscale eddies are sitting literally in the middle of that kind of energy cycle between the very large scale and the very small scale. Overall, they're a pretty big player because they can extract energy both from available potential energy and kinetic energy. So pretty important in both cases. They form the bulk of the kinetic energy in the ocean, but they can also transfer kinetic energy across scale. So in that diagram again below, we have mesoscale eddies sitting in the middle. They can convert from available potential energy into kinetic energy via baroclinic instability. And on the bottom arrow, they can also be part of this kind of energy of inverse cascade or backscatter, taking energy from the small scale into the large scale. So they have this kind of dual role to some extent, can play with energy across scale and across reservoirs. So being able to actually represent that in simulations is quite an important aspect. So probably one of the most successful parameterization in terms of mesoscale eddies has been Jet McWilliams, going back to 1990, that mimics baroclinic instability. And it's been extremely successful in models that are on this range on the right, where the scale of the resolution of the model is much larger, or is larger than the deformation radius. So Jet McWilliams basically mimicked baroclinic instability, and they were able to reduce quite successfully spurious convection and mixing in coarse resolution model. And was acting as a net sink of available potential energy. However, one aspect of that parameterization doesn't really account for that eddy energy that is being extracted from the potential energy reservoir. And that could cause some issues because we're not accounting for that amount of eddy energy that is being extracted. So people have been working on keeping track of that eddy energy in the last 10 years or so, with one idea that's been quite successful, which is coming up with a prognostic equation for the eddy energy, and can be written in 3D or in 2D as kind of vertically integrated, and it can include eddy energy, eddy kinetic energy, or eddy kinetic and potential energy. I'm sure David Marshall will talk about this in his talk. So we can write an equation where E here is the eddy energy. So the rate of change of eddy energy is equal to sources and sinks and transports, which I'm sure Ian will talk about, of eddy energy, and being able to close the eddy energy budget with such an equation. People have been using that equation to inform the Jet McWilliams parameterization and its coefficients. And again, I'm sure David will talk about this in its geometric presentation, can be very successful in closing the eddy energy budget by informing the Jet McWilliams parameterization in this way. But it's not enough to some extent, because we're still missing some energy pathways, such as the inverse cascade of energy or the transfer between available potential and resolved kinetic energy. We also need to think about the fact that now we're not at very coarse resolution in terms of our global models. Some of our simulation are what we call eddy permitting, so they're sitting at the resolution of the deformation scale. So we need to think about this kind of resolution-aware parameterization of eddies. And lastly, we also need to rethink our momentum closures, both for this idea of a backscatter or an inverse cascade of kinetic energy, but also because so far all of our momentum closures are viscous. They just assume that momentum is just being dissipated to some extent, and we know it's not true because we know eddies can in general create a gradient momentum fluxes. So we need to think about all those new pieces together. So two pathways that we need to consider. One is the transfer of available potential energy into resolved kinetic energy, especially in those kind of eddy permitting model and those coarse resolution models sitting at the boundary, and the backscatter or inverse kinetic energy cascade. So I'm going to show a few examples. And the first one is going to be this transfer of potential energy into resolved kinetic energy. So two new schemes kind of got published last year, and they were pretty much new at the Tallahassee meeting, one from Scott Bachman, another one from Malte Jensen and co-authors, trying to do exactly that. basically taking the available potential energy removed by the Gent-McWilliams and feeding it into the resolved scale. So both mimicking Boltzmann instability and this energy backscatter. So the first plot I'm showing here is from Bachmann 2019. At the top, so in all those figures, we're seeing the kinetic energy. In the top row, this is the kinetic energy when the simulation only has Gent-McWilliams on, and we have 3 different resolutions depending on the deformation scale. And at the bottom is when Scott's parametrization is included, meaning that the available potential energy removed by Gent-McWilliams is fed into the barotropic mode in the momentum equation. So all of that is included. So what you can see in those bottom plots is there's more resolved kinetic energy. So parametrization is quite successful in achieving what it's supposed to do. Second paper, which basically has the same spirit from Malte Jensen and co-author, has a little trick in the middle where they still re-inject that lost energy from Gent-McWilliams, but they use a prognostic eddy energy equation to do that. And so the plot at the bottom shows the kinetic energy spectrum as a function of wave number, and the curves that you want to look at really is the blue curve in the middle compared to, say, one of the green ones, which will have only Gent-McWilliams for the green, and the backscatter and this kind of transfer of available potential energy into a resolved scale being the blue one. So basically energizing the flow and getting it closer to what a high resolution should be. Now, both of those parameterization assume that in the momentum equation, the flow should be re-injected using a term that looks like anti-viscosity. And the main question is it appropriate? Is it the most appropriate form for momentum closure to just be negative viscosity multiplied by a Laplacian? There's been it's a possibility, but it might not be the only one. There have been a few stochastic closures being proposed as a different way to close the energy in the momentum equations. And also more recently, we had an idea where we use non-Newtonian closures. So they use basically the rate of shear and strain as a way to mimic the sharpening of jets and gradient momentum fluxes, and they have the advantage of being scale and flow aware. So we show in idealized simulations, and I'm showing transfer of energy on the right. So we can just concentrate on, say, the top plot, which is the high resolution. The violet curve shows the inverse cascade of kinetic energy in that high resolution model. In the middle is an eddy permitting model where that curve is now weaker. So we have less inverse cascade. And when we put our parametrization at the bottom, then the inverse cascade is amplified, kind of mimicking what a high resolution simulation is doing. So a new way to actually mimic the backscatter of kinetic energy using this type of parametrization. So overall, we know that a lack of physically consistent energy cycle does impact the ocean circulation in simulations, both idealized and global. There have been a few eddy turbulence closures that targeted the energy transfer, both between scales and between reservoirs, and they showed a reduction in biases in transport, but they've only been tested in idealized simulation, and we've only just started putting them into global models, and as part of the CPT, this is something we're going to do a bit more rigorously. And what's important is also thinking about the challenges ahead. And one of them is, can observations and global high-resolution simulation help constrain the partitioning of energy and its pathways to help us discriminate between parameterization and make them as robust as possible. And I know Sylvia will talk about this at the end of today. Also, the question is which momentum closure should increases the fidelity of the energy cycle, and that's important to keep in mind. And last point, which hasn't been talked about a lot, is the vertical structure of eddy energy. We know very little about it. Does it matter? We think it does, but what type of impact will it have on transport? And that's something we need to think about as well as we move forward, just in general as a scientific question, but also as part of the CPT. So overall, I think there's been a lot of progress, and we're very excited to do more. But there's still a pretty big need to have something that is observationally constrained, unified in terms of buoyancy and momentum, in a way that the energetics remain our target in a sense, we could have something that is robust, scale-aware, flow-aware, and being implemented in global model to reduce biases in transport and large scale. Thank you very much.
Thank you, Laure. I think we have a few minutes to take a couple questions. Reminder, if you have a question, just unmute yourself and speak up, or you can type it into the chat box and I'll ask it out loud for you. So any questions for Laure? Okay. So I don't see anyone with any questions. With that, I think we'll move on to our next speaker, which is Ian Grooms. Okay, go ahead, Ian, and thank you, Laure, for your presentation.
Okay, can you hear me?
Yep, go ahead.
Jenny, can you hear me? All right. Thank you. Thanks to NOAA and NSF for supporting us, and also to Jenny for setting this up. So, ocean mesoscale eddies is the heart of this talk, energetics of the eddies. But I want to talk a little bit about the tracer transport first, so that I can contrast with the energy transport. Obviously, mesoscale eddies transport tracers. If you throw a Lagrangian float, a drifter, out into the ocean and track it, you'll get a track that looks like what I've shown in this figure here from Bertie et al. 2011. It's quite wiggly, as you can see. So it's not just following the path of the mean currents, but it's being randomly advected around in sort of a loopy structure. And if you wait long enough, if you kind of squint your eyes, these trajectories look like random walk trajectories. They look like, qualitatively, like the particles of pollen in a fluid, Brownian motion, the characteristic example of diffusive transport. There is in fact a mathematical theory for this, connecting transport by a turbulent fluid with diffusion, and the theory assumes that the turbulence that's doing the transport is statistically homogeneous. So no matter what part of the domain you look in, the energy is the same, the temporal spatial correlation structure is the same. And under these assumptions, you can derive a relationship between the rate of turbulent diffusion, the diffusion coefficient, and statistics of the flow, mainly the kinetic energy and some sort of a decorrelation time. If you want to, you can formulate this in terms of the kinetic energy and the length scale using a mixing length, but in both cases, the kinetic energy of the flow is obviously important for the rate of transport. So in models that don't resolve the eddies, or that imperfectly resolve the eddies, we need to parameterize this transport. And in order to do so accurately, we need to know the energy of these eddies. There's a little caveat here. The ocean is not homogeneous. There's significant differences in eddy energy depending on where you look, but it's fairly appropriate to make the approximation that the flow is locally homogeneous. So the energy doesn't vary much over a grid cell, and then the transport, the diffusive transport in that grid cell, is driven by the local energy in that grid cell. So Laure had this equation up much more nicely than I do. Generically, you can write down a budget for the eddy energy. And so if you look at some kind of a control volume, say a grid cell, the rate of change of the eddy energy within that grid cell has to be driven by sources and sinks, and then transport into and out of that control volume. The Nemo Ocean model has an equation like this. Pardon me. And it tracks mesoscale eddy total energy. The MOM6 ocean model has an equation like this that tracks mesoscale eddy kinetic energy. And as Laure suggested, the focus of this talk is on the transport part of that budget. It's nice to start with theory. If there's any theory that will tell you what the transport looks like, it's good to know it. Unfortunately, there isn't much theory for transport of energy, unlike transport of tracers. You can do just a scale analysis on that kind of a budget to see how big the different terms are, sources, sinks, and transport. And that kind of analysis does say that in certain regions of the ocean, the transport won't be negligible. It's not going to just be a local balance between sources and sinks, but energy will have to flow out of some regions and into others. But that theory doesn't tell you anything besides the amplitude of the transport and the fact that you can't throw it away. There is theory for energy transport by Rossby waves. It's a special case of the theory for transport by waves generally. And Karsten Eden and Dirk Olbers have recently written a model that uses linear Rossby wave theory to parameterize the energy transport. And this is appropriate in regions of the world ocean where the mesoscale eddy energy is acting like a superposition of Rossby waves. There are other regions, of course, where the energy of the eddies is quite high and they don't act like Rossby waves. And so in those regions, it's still unclear. There's no theory telling us what the transport should look like. Now, we do have excellent observations of these dynamically coherent mesoscale eddies, and it would be really nice if we could come up with some way to connect those observations of the eddies, for example, from satellite altimetry, to some theory of energy transport. That has not been done yet, but it is a tantalizing prospect. This figure is just, I've pulled from Shelton et al.'s 2011 Progress in Oceanography paper, and it shows red and blue tracks of mesoscale eddies identified from satellite altimetry. Red and blue are cyclonic and anticyclonic, or the other way. Blue is cyclonic, red is anticyclonic. And this is just to show that we have a lot of data, and it would be great if we could come up with a theory to connect this and give us predictions of energy transport. There is a bit of a caveat that you can't treat energy transport in the same way as you treat tracer transport from what I showed on a previous slide, because the tracer transport theory assumes that the tracers are being transported by a field of turbulence that is statistically homogeneous, that doesn't have variations of energy from one place to another. And of course, if energy is being transported, then it has to be different in one place to another. But there's potential for some theoretical advancements here. All right, so as I said, you've got the geometric model in NEMO, and Laure mentioned, and the Miki model in MODEM 6, and they've both been implemented and run. And so even though there's not much theory to say what the transport term should look like, they are using some model of that transport. And the model that's being used is diffusion with an additional background advection, and in the case of geometric, with a bit of a Rossby wave flavor thrown in as well. One thing that we can do is at least just to test if diffusion is appropriate in the absence of advective and Rossby wave type effects. One way to do that is to set up a process study. So rather than using observations or global realistic simulations, we can condense down to an idealized model and just study the process. And one way of doing this is to set up a simulation where you force energy within some sub-region of the domain, and then you watch and study how the energy spreads from that region where you're forcing high energy into the regions where you're not forcing the energy, or where there's less energy. And in this figure, there's no forcing outside of the black circles. So all of the forcing is inside of the black circles, and the energy is spreading outwards. On the left, we're on an F plane, so the eddies don't know about the curvature of the Earth. on the right, we're on a beta plane, so the eddies do know a little bit about the curvature of the Earth, and you can see there's differences between these. To summarize the results from those kinds of studies so far, the energy transport is diffusive on average, so that's good. The geometric and Meeke models are using something that is appropriate, at least on average. The rate of energy diffusion is, interestingly, about 75% of the tracer diffusion, and that's actually a fairly highly accurate number, 75%. It's not sort of 75 plus or minus 10. It's quite close to 75, which suggests that there may be some theory there, and also underscores the fact that energy transport is not the same as tracer transport. When the curvature of the Earth comes into play via the beta plane approximation, the eddies respond to that by reducing transport in the meridional direction. There's open questions there as to how much it's reduced and what are the various scalings, but at least we do know that it's reduced in that direction. Some drawbacks or some open questions are that the energy transport only looks diffusive on average. So if you wait for hundreds to thousands of years and average over very long time scales, you get a very nice fit to diffusion. But instantaneously, the eddies themselves are wandering around in a sort of semi-random manner. And so the instantaneous transport of energy that's associated with these wandering eddies does not look diffusive. And it may be valuable to come up with a stochastic model or a model that is a more accurate representation of the instantaneous rate of energy transport. Another drawback or still remaining open part of these investigations is the impact of ocean floor topography and of boundaries like continental shelves. So the effects of bathymetry topography on energy transport has not yet been studied, and it's not clear how best to incorporate those effects into the models, into the Meeke or the geometric models. That's all I have.
Great. Thank you, Ian. Any questions for Ian?
Ian, this is Baylor. I was interested in how extensively you've explored the 75% varying the length scale of beta or the length scale of your forcing patch versus the deformation radius.
Yes, so I have not introduced beta into those. So the 75% is on an F-plane. Introducing beta, I have not figured out completely the importance of beta in the absence of tracer. So that's still open. And then I should also point out these idealized studies remain at this point barotropic. So there is no deformation radius here, the purely barotropic flow. And so adding in and saying, what is the impact of stratification via a deformation radius is another open part of this.
Ian and Laura, this is Simon here. Laura, you referred to getting a handle on energy in IPCC class models, and I wonder, Ian, your take, or both of you, is this something we're going to see in 7 years from now, or do you think the progress is slower than that?
So you're talking about including energetics into the IPCC class model? Is that, sorry,
yes.
Did I hear correctly?
That's correct.
Yeah, so I mean, of course, our goal within the CPT is to implement a lot of those kind of new energy-related closures within global simulations. So I don't know if we're going to make it for the next CMIP, but I'm hoping that by the end of year 2 or 3, we'll already have, at least a few, let's say, eddy constraint parameterization within the models. And as Ian mentioned, Nikki, for example, is already in MOM6.
Yeah, and if I can
Please
follow on to that. So if you think about, for example, the history of the Jen-McWilliams parameterization, it went into the global ocean models fairly quickly and is still in them. It has remained in them and has led to improvements. But there's, of course, still open questions with regards to the best way of configuring a GM parameterization. And by analogy, these models already exist. They've already been implemented and they're running, and we expect and hope that they will lead to improvements in the near term. And what I've focused on in my talk is sort of some of the longer term questions, maybe as far as getting it to be just perfectly correct. That may take some more time, but I do think in the short term that there is a lot of improvement to be had, and things have already been implemented, and we're already working on that.
Correct. Yeah. Thanks, Ian, for that. Indeed. So I mean, I assume you only talked about Nikki, so sorry about that, Simon. But indeed, a lot of the parameterization that I mentioned in my talk have been implemented into MOM6. So our momentum closure is in MOM6. The Jen-McWilliams and backscatter is also in MOM6. So I really see a path forward that will be short term for many of those studies to actually be in global models and run at the global scale.
So David here, I was going to ask a question to Ian, but can I first just pick up on the last point and say for geometric is in NEMO, and the plan is to make it the default eddy parameterization over the next few months or so, as soon as the work is published. So I think there is a roadmap to getting some of these schemes out pretty quickly, actually. My question for Ian is, I don't know if the two pictures you showed on the F-plane and beta plane of the eddy spreading were at comparable times, but I had the impression the zonal spreading was somewhat suppressed too on the beta plane. Could you comment on that, please?
All guests have been muted. You can unmute your line by pressing *6. All guests have been unmuted.
Oh, God.
All guests have been muted. You can unmute your line by pressing *6.
Yes, so these two simulations are not directly comparable. I believe that the forcing length scale is slightly different between them. They've also both been run to a statistical equilibrium already. On the left, or you said, is the zonal transport also reduced? And I did not see that, actually. I think the difference here is probably going to be that the total amount of energy forcing in the figure on the right is reduced. So there's just less energy in the figure on the right compared to the one on the left. But I don't think that the zonal transport is reduced.
Okay, and we had one question on the chat box. I'm not sure if you answered already, but Alice Barthel asked, have there been idealized studies with anisotropic background flow?
No. So on the F plane, there's no imposed background flow, and the dynamics don't generate one by themselves. On the right, on the beta plane, again, there's no imposed background flow, but the flow rectifies a time mean flow in the background. And it's got a zonal jet to the right, eastward jet in the center of the domain with sharper return flow to the north and south. And so that has been taken into account in the idealized simulation on the beta plane, but I have not explored imposing an anisotropic background flow.
Great. So I think we should move on to our next speaker. Our next speaker is Stuart Bishop, I believe. Yep, go ahead, Stu.
Okay, thank you. Can you hear me?
Yep, we can hear you.
Okay, great. So this is work I've been doing with my graduate student, Amin Guo, and Justin Small and Frank Bryan at INCAR. And so we're interested in how air-sea interaction at the mesoscale modulates the baroclinic instability mechanism of converting mean potential energy to eddy kinetic energy. So this is motivated in large part by this Kurtman et al. 2009 paper showing air-sea interaction in two coupled climate models, one on the left in your standard 1 degree resolution climate model, and on the right in a 10th degree resolution coupled climate model. And what is plotted here is the correlation between the sea surface temperature and the turbulent heat flux, which would include latent and sensible added together. And there's important aspects that show up in the coarse resolution model. You have high correlation in the tropical Pacific and not really anywhere else. There's some spurious correlation in the high latitudes. However, when you move to the high resolution model, you find that the regions in the western boundary currents, such as the Kuroshio extension in the North Pacific, the Gulf Stream and the Atlantic, and portions of the Antarctic circumpolar current now have high correlation between the sea surface temperature and the net heat flux. So one of the things I've been asking myself is, so what are the ramifications for this correlation in the high resolution models? And we can look at this from a Lorentz energy cycle. I put the equation up for those who are interested, but you can also look on the bottom left. This is a standard Lorentz energy cycle, just focusing in on the eddy potential energy part of the budget. You can imagine that you have a reservoir of eddy potential energy, and then the source of this eddy potential energy is going to come through baroclinic instability through down gradient eddy buoyancy fluxes, and this is converting the large scale potential energy that's generated indirectly by the wind and directly by the surface buoyancy forcing. This eddy potential energy can then be further converted to eddy kinetic energy through this PKC term, which is through internal eddy or vertical eddy buoyancy fluxes. And what we're finding, there can be dissipation as well, but focusing mainly on the air-sea interaction term, that this feedback related to sea surface temperature and net heat flux anomalies can potentially modulate the energy available to be converted to eddy kinetic energy. So it's important, though, however, to define what you call an eddy, which is going to come up because there's two conflicting studies in the literature, and I think in how you define what you call an eddy sort of rectifies this difference. So what we're going to call an eddy is any deviation from the monthly mean climatology. So this is going to include all transient motions associated with internal variability, such as waves, meanders, cold and warm core rings. And what this does not include is an average seasonal cycle, which is a forced pattern. So as an example, on the left here, we have the mean sea surface temperature from climatology. I think this is January. And on the right is a snapshot in January of an eddy portion. So it's much smaller, but you have plus and minus 4 degrees C or so. Now, the air-sea interaction term is source or sink. So from a study in 2016, model shows that from a regional coupled climate model, that the Kuroshio extension region has a significant sink of eddy potential energy due to the air-sea interaction. And they did this, they found out the sink through doing smoothed and unsmoothed coupled experiments where they smooth out the eddy field before it interacts with the coupling. And then they found that when they smooth out the eddy field, that you dramatically reduce this air-sea interaction term, and that baroclinic instability is actually a more efficient process versus the unsmoothed experiments that include the eddy variability. However, before this study, in which I've actually, I calculated these potential energy sink terms, and I went straight to the von Storch paper in 2012, and I had a very different picture of what this term comes out to be. And so as you can see in their study, that the potential energy is actually a generation term through this air-sea interaction. And so mainly it's going to be in the northern hemisphere. And the major difference is in their definition of what they call an eddy, which includes the mean seasonal cycle. And so I've set out to try and estimate this term in coupled climate models and in observations. And so on the left and on the right, on the left we have Geophoro version 3 combined with MIMOC climatology for mixed layer depth. This is a 1/4 degree product, and we have sea surface temperature and net heat flux as a contributor there. And on the right we have a high resolution 10th degree version of the community Earth system model that was run for 100 years. This is coupled with a 1/4 degree atmosphere model. Just for comparison, I calculated the eddy potential energy of the mixed layer, which is something we can calculate in observations, which is just proportional to the sea surface temperature gradient if you don't include sea surface salinity contributions and freshwater fluxes. And we have a bit higher eddy potential energy in the model, but we still don't understand why. So when we take the observations and we do a 3-way decomposition of the Reynolds averaging for the potential energy generation term, we find that you have 2 terms that emerge. You have a seasonal term, which is what we're trying to remove in order to isolate what is happening due to transient motions due to internal variability. And that's very large in the North Atlantic and the North Pacific, but not really prevalent in the Southern Hemisphere where there's not as much of a seasonal cycle. But on the right, the transient term shows up as a sink in your particular hotspots for ocean eddies, such as the Western boundary currents in the North Pacific and Atlantic, and in the Antarctic circumpolar current. There is a bit of variability associated with the tropical Pacific, and we've looked into this, and it has a lot to do with the El Nino Southern Oscillation. And once that is regressed out, those timescales are removed, and it does not show up much as a sink. So the sink is about 1/10 of a terawatt. And so if you were to add the seasonal term to the transient term, you can get back what was found in von Storch. So we're sort of pointing out that this 3-way decomposition is essential if you're going to isolate the impacts of internal variability on eddy potential energy sources or sinks due to air-sea interaction. We further looked at the scale dependence of this eddy potential energy sink, and on the left we've calculated the potential energy sink as a function of space scale on the y-axis and time scale on the x-axis by smoothing out the field spatially and temporally. And you can look at this as a ratio of the unsmoothed potential energy sink. So at 0 time and space scales, that is the full signal. And so that should converge to 1. And as you move out in space and time, you diminish the available energy through this term. And we find that about 50% of the energy is confined to spatial scales less than 2 degrees and less than annual time scales. And we find this both in the high resolution model on the right, except the high resolution model tends to smooth out much quicker. But it's also interesting to note that there's a lot of mesoscale energy, sort of when you look at less than 2 degrees, there's a lot of energy that's still spread out into interannual timescales, sort of pointing to modulation of mesoscale eddies. That we see this a lot in the Kuroshio extension, where it has this bimodal state between strongly and weakly meandering states every few years or so, tied to the Pacific Decadal Oscillation. So some future studies that my graduate student and colleagues are working on is how can we effectively sort of develop a way that we can inform sort of the people who work on parameterization, sort of how we might be able to look at this problem through adding these parameterizations into the coarse resolution models, which are currently not there. So we're trying to develop also a methodology for comparing high resolution coupled simulations. And we think one way we can do this is look at something we're calling a baroclinic instability efficiency parameter. So if you take your Lorentz energy diagram here on the left, we have our three sources and sinks, mainly one source through baroclinic conversion. And so if you divide through what's going in to what's leaving through that's being converted to eddy kinetic energy, you can also show that this is equal to 1 minus the sink due to air-sea interaction divided by the baroclinic conversion term. So this is basically looking at what is the fraction of energy that's removed through air-sea interaction. And my graduate student and I have done some preliminary work looking at observations and the CESM high resolution version. So this is just an upper ocean estimate of the baroclinic instability efficiency. And on the top, we have a combination of GFRO, the Aviso, and MIMOC product to estimate these different sources and sinks. So on the left, we have the sink of energy due to air-sea interaction. In the middle, we've estimated baroclinic conversion terms from the sea surface temperature and Aviso field. And if you calculate this efficiency parameter, you can find that it's anywhere from 25 to 75% efficient. And when you look at the bottom row, for the same region in the high resolution model, we get similar sort of background flow, a similar conversion rates, but we have differences in the efficiency parameter. And so it's pretty efficient leaving the coast, but downstream, you have a little bit less efficiencies, pointing to a stronger air-sea interaction sink. And so we think that this may be a way that we can compare against a lot of different high resolution models, which this doesn't depend necessarily on the absolute energetics, but which can vary widely between model simulations. So in conclusion, we find that mesoscale transient motions at the air-sea interface are responsible for moving about 0.1 terawatts of eddy potential energy that could otherwise be converted to eddy kinetic energy. And by including a mean seasonal cycle in your definition of an eddy, that this doesn't necessarily reflect the true nature of mesoscale eddies as internal energy processes. And the sink of eddy potential energy is really confined, about half of its sources in the 2 degrees or less in spatial scales and less than annual timescales. Sort of future directions are sort of coordinate and help to develop parameterizations of this sink in coarse resolution climate models and explore this efficiency parameter across a wide stretch of high resolution models. And with that, I will take any questions. And I'd like to thank NASA and NCAR for their support in this work, and US CLIVAR for the awesome workshop last March.
Great. Thank you, Stu. Any questions for him? I think we have time for one question, maybe. All right, I don't see anyone speaking up, so I think we'll go on to the next speaker, which will be David Marshall. Right, go ahead, David.
Okay, well, first of all, thank you, Jenny, for organizing this meeting. And thank you indeed to Jenny and the other CLIVAR, the rest of the CLIVAR team, and also the organizers of the meeting for an excellent meeting last year, which was very enjoyable and highly productive. So I'm going to talk today about geometric. So this is our project that's been ongoing for more than a decade now, looking at the geometry and energetics of ocean mesoscale eddies and their representation in climate models. There have been an awful lot of people involved over the years. So the key players for what I'm going to present today, apart from myself, Julian Mack, who was a postdoc with us for a number of years, now at Hong Kong, University of Science and Technology, James Madison at the University of Edinburgh, and also Scott Bachman not NCAS, sorry, that's my mistake, NCAR. So I'm going to talk about why eddies matter, in particular in the Southern Ocean. I'm going to talk about our new approach, geometric, and then we'll talk briefly about how you implement in a general circulation model and our future plans. Okay. So I've not got long with 10 minutes, so I thought I would just show one slide to motivate why eddies matter. And I think this is a very nice example because it shows a known systematic error in non-eddy permitting ocean climate models. And this is the phenomenon of eddy saturation. So sometimes when I put this slide up, it provokes a lot of heated discussion because people hold quite strong views about eddy saturation and which parameterizations can or can't capture saturation. But nevertheless, I think it's generally true that if you blow a wind stress over a model of over a sudden ocean model, then what you find is that as you increase the wind forcing in a model with parameterized eddies, and here this is a 2-degree model with Gentleman-Williams, that we find the circumpolar transport increases with the wind forcing. And in contrast, when we get to 1/6 of a degree, which is certainly not eddy resolving, but at least permits some eddies, we find that in this particular model and in many other models, there's a massively reduced sensitivity of the strength of the circumpolar transport to the strength of wind forcing. Now, this matters not just for the circulation of the Southern Ocean, it really matters for many climate metrics. And that is because the strength of the circumpolar current, or more strictly the thermal wind part of the circumpolar current, is strongly tied to global stratification. So if we think of the atmosphere as somehow imposing the north-south temperature gradient across the Southern Ocean, then the circumpolar current essentially maps this surface stratification onto a vertical stratification to the north. And this goes back to the ideas of Anand Ganadesikan and many others over the years. So Southern Ocean eddies are important for setting global stratification, equilibrium ocean heat content, equilibrium atmospheric CO2, because the ocean stratification has a large impact on the carbon budget, climate system. And in a transient sense, it's likely to have an impact on heat and carbon uptake, on centennial timescales, global sea level change. And in fact, in some models, we found also even sets the adjustment timescale of the global ocean. So this is a process that's, Southern Ocean eddies really do matter, I believe, for climate, and especially on centennial and longer timescales. Now, geometric is actually a very general framework rather than a parameterization. It's a framework for parameterizing and interpreting ocean eddy mean flow interactions. And our key idea was to try and preserve analogs of all the key relevant conservation, in particular conservation of momentum and energy. So I'm only going to show you the very simplest version of geometric today. So if we look at the mean momentum equation, essentially we introduce a force into our momentum equation, which is d by dz as some eddy stress. And the effect of this eddy stress is to transfer momentum vertically, so typically from the sea surface down to the sea floor, where it will be removed by pressure gradients across topography. But the important point is that this eddy force will extract energy from the mean flow, and if we include backscatter, indeed could return energy to the mean flow. So we need to keep track of the total amount of energy in the system, and so we introduce an eddy energy budget, and we have d by dt of this new variable, the unresolved eddy energy, is then given by the various terms in dots that are the sort of terms that Ian talked about, the flux energy through the ocean, but in addition, including a mean eddy energy conversion term to take up the energy lost from the mean flow. So by construction, the total amount of energy in the system, in the model, is conserved. Now, although we're not wedded to Gentleman-Williams in the long term, in the short term, we also take a pragmatic viewpoint, and the vast majority of models use Gentleman-Williams at the moment, and Gentleman-Williams indeed leads to many desirable properties in ocean models. And so we ask the question that if we force geometric to look like Gentleman-Williams, then can we reverse engineer out an eddy diffusivity? And the answer is yes, and it takes this form on the right. So kappa is a non-dimensional number alpha, which we know is less than 1 in magnitude, times the buoyancy frequency, times the eddy energy, and I should say that's kinetic plus potential energy, divided by the mean buoyancy gradient. Okay, now I want to stress this is a rigorous mathematical result. So if we know the eddy energy and we will know the stratification parameters, then the only freedom left in our parameterization problem is to specify this non-dimensional number, alpha. So I'm going to show you 3 proofs of concept. The first is the linear instability problem. So this is an esoteric example, but it is an analytic solution. So if we give ourselves a baroclinic shear flow, so a flow that increases with height, for example, modeling the Southern Ocean circulation with a uniform shear, and we assume uniform rotation, etc., then the most unstable mode has a length scale of the deformation radius, and we can calculate the growth rate for that most unstable mode. And we can also attempt to parameterize this problem using geometric. And what we find, to cut a long story short, is that eddy energy in geometric grows at a rate that is the eddy growth rate if we choose alpha to be 0.6. And I want to stress here that we have not put the dimensional part of this answer into the problem, but rather we've left enough information in the underlying equations that it still knows about the dimensional form of the eddy growth rate. So our only freedom again is to parameterize alpha. Now in reality, of course, the system is highly nonlinear. The eddies are turbulent. And so we need to move to a nonlinear eddy permitting ocean model. And Scott Bachman, as part of his PhD, had set up this beautiful channel model experiment in which he looks at the spin down of a baroclinic eddy type front. So this was originally designed for the surface mix layer. We're applying it over the full ocean depth. And what Scott did was to let the turbulence develop. He then drops various tracers into the channel to diagnose the eddy diffusivity, and then we can compare with various predictions of different parameterizations. And so what you see on the right is our diagnosed eddy diffusivity on the x-axis against the predicted diffusivity on the y-axis. And I'm just showing one example here, which is a little unfair on Baylor because Fox-Kemper et al. Is designed for the surface mix layer. We're here applying it over the full ocean depth. But you can see that this particular parameterization does not give us a good fit, which would be the dashed line with slope 1. And in contrast, geometric, if we just set alpha to be a constant, 0.2 in this case, then we get a vastly improved fit, and in fact a much improved fit over any other parameterization that we've tested in this model. If you look more carefully, then you see that the line actually doesn't quite have a slope of 1, so at low values, in fact alpha we already know from the linear eddy problem should be 0.6. Whereas we've imposed 0.2. So you get discrepancies of the order of factors of 2 or 3. But across 4 orders of magnitude, I would argue this is a very good fit indeed, compared to any other previous parameterization. And then the third proof of concept, it turns out that in geometric we can reproduce and explain physically this process of eddy saturation. So to remind you, we increase the strength of wind forcing over an idealized Southern Ocean channel. And with explicit eddies, we find that the circumpolar transport is insensitive in this model to the strength of wind forcing. And if we look in geometric, which is the red line here, and also the purple line, they're 2 different types of geometric. You can see that we basically reproduce the correct answer. So we get the right strength for circumpolar transport, and we find in leading order that that there is very little sensitivity of the circumpolar volume transport to the magnitude of the surface wind stress. So one of the nice things if you have a parameterization is you can delve down and ask, well, what's the physics of that result? And well, it turns out it's very simple. You need to think about the momentum budget and the eddy energy budget. So back to the conservation laws. And the momentum budget in the Southern Ocean is essentially between the wind stress at the surface and the bottom form stress. So this is the ocean circulation pushing against topography, transferring momentum to the Earth. But the challenging part of the problem is getting momentum down from the surface to the bottom. And this is done by an eddy form stress. And I see I'm almost out of time, so I will say when geometric eddy form stress scales with eddy energy. And so the momentum budget sets the energy. And then if you look at the eddy energy budget, well, the source is the shear times the eddy energy, the eddy growth rate times the eddy energy, and the sink is going to be the eddy energy times a damping rate, we assume set by bottom drag, Lee wave radiation, or other processes. And so the eddy energy budget sets the strength of the current. And there's even a counterintuitive result, which we've confirmed numerically, that as you increase the drag, the current gets stronger, not weaker. And that's because the effect of friction is to kill eddies. And so I'm going to wrap up there. We have put geometric into the NEMO model. The results are not yet published, and this is a public domain talk, and I thought it was better to leave those results out for now. But I've talked about the geometric framework. I've got just one picture from NEMO here on the right showing a preliminary solution for the eddy energy. But it's very simple to implement in a GCM. It's just a modification to the Gentleman-Williams eddy diffusivity, and you need one additional routine to solve the prognostic eddy energy equation, which we do for the depth integrated eddy energy. So it's a 2D solve. And in the future, we have many plans, including eddy permitting resolutions, looking at Reynolds stresses, a lot of work on the eddy energy budget. So we're involved in work of the type Ian was talking about. I'm quite excited about extending this to include the effects of variable topography and PV closures and so forth, and also applying to the sub-mesoscale. So I'll wrap up there. Thank you.
Thank you, David. Any questions for him? Great. So I don't see any questions either for David. We'll move on to, do I hear someone? Okay. We'll move on to our next speaker. It'll be Eric. Okay, go ahead, Eric.
Good afternoon, everybody. So what I'd like to do is to report on one aspect of a model and comparison project that took place within the framework of the CLIVAR Ocean Model Development Panel. And the co-lead of this paper are Steve Yeager and Baylor Fox-Camper, assisted by many of the developers or people who've run the various models that are part of this presentation. So a little bit of a background, a key decision. I think a lot of the talks before is just, what is the spatial resolution of each of the components. Back in 2006, Steve Griffiths and others put together basically a description of the parameters of what is it that we would need to look into an ocean model intercomparison project as part of CMIP6. And in this case, the essential element behind the OMIP is a common set of atmospheric and river runoff data sets that can be used by many of the models. So it's an outcome of the core experiment that used the atmospheric river and river runoff of Large and Yeager, and quite a lot of models participated in that effort, and here's a list of the publications that came out of it. But this data set has not been updated since 2009, and a new data set made by Tsujino et al. Was recently developed and based on the Japanese reanalysis GRA55, so that we can update it regularly and all the way to the present time. So Tsujino recently submitted a paper to GMD that compared the evaluation of the simulation of the models that are used in many of the CMIP6 models, comparing the core forest, which we call OMIP1, and the OMIP2 simulation that used the GRA55 DO data ocean forest, and using the metrics that we use on a regular basis. So Tsujino et al. Found still some remaining bias that could not be really attributed to the forcing, and many of which are expected to be mitigated by using finer horizontal or vertical resolution, or maybe this is shared bias in the atmospheric force. So the goal of this exercise, and that's a full paper, has been submitted to GMD, the same, and is to assess how robust the climate relevant improvement in ocean simulations in the mean and the variability associated from increasing the resolution from coarse, which is on the order of 1 degree, to eddy permitting, eddy resolving / 1/10 of a degree. And all those simulations are using the same atmospheric forcing. So here we'll focus on 2 elements. If you want to know more, we can I can refer you to the full paper. So the configuration is, since the goal is to identify the differences, most of the modeling groups configure the high resolution with very similar parameters to that of the coarse resolution configuration. At the present time, given that they are quite expensive, we have only 4 groups that participated, one using the model, the HICOM model. So at Florida State, POP at NCAR, FESM at the WI, and LICOM in IAP in China. The reason I put absolute versus relative wind stress in parentheses because it's going to matter. Absolute wind stress means that the the stress is computed, does not take into account the shear between the wind speed and the ocean current. So HICOM is the only one using the absolute, all the others are using relative wind stress. All simulations were run for 1 cycle and of the GRA DO, the GRA 55 forcing. So here what you see is pretty much, after a little bit of a 10-year spin up or less, the total kinetic energy settles down, and on average, as you expect, the high resolution configurations show higher kinetic energy, and there's a significant increase from the coarse to the fine mesh. The blue line is a HICOM with the absolute wind, and this one is higher than the next one, which is the NCAR model, because of the main differences between absolute and relative wind. Since it's been shown that when you use relative wind, you decrease the kinetic energy by about 30%. A similar run done at NCAR with absolute wind raises the level of kinetic energy to about 35, which is similar to a HICOM. The LICOM is the lowest energy, and then the FESM is in between. FESM is a little bit different than the others in the sense that they use variable grid. Therefore, what they call the high resolution still has a low resolution component elsewhere. But on average, going from 1 degree to 1/10 of a degree, you triple or quadruple the kinetic energy, except for FESM, which just only doubles, probably because of the variable grid that they use. So 2 main impacts of increasing the resolution. First, the solution becomes more nonlinear, therefore you have a better representation of the western boundary currents. And also the first Rossby reducer deformation is resolved throughout most of the domain. So here what you see is a mean sea surface height field focused on the North Atlantic. At the top is the best estimate for the mean sea surface height field. That's based on the work of Rio et al. In the middle, you have the high resolution simulation, and on the lower panels are the coarse resolution. So western boundary current in the coarse resolution models are always diffuse and do not separate, especially Gulf Stream from the coast. That's a well-known result. It's significantly improved when you go to 112, but the results are quite a little bit uneven, especially if you consider the North Atlantic current. If you look at the lower 3 panels on the right, for POP, FESM, and LICOM, they have a Gulf Stream past that is extremely zonal and does not really represent the North Atlantic corner at all at coarse resolution. When you go to higher resolution, there's a slight improvement, but still the Gulf Stream is still very zonal. For some reason we don't fully understand this, HICOM, both at the coarse and the fine resolution, are able to represent the North Atlantic corner. So summary, I mean, for this part, the horizontal research does improve the Gulf Stream separation, but not necessarily the northwest corner. And since they all use the same atmospheric forcing data sets, we think that the difference is most likely due to the numerical and physical choice made by each of the modeling group. Anyway, this is one outcome that needs to be further investigated. Now, if we look a little bit at the sea surface height variance, as you expect when you move from the low risk, so at the top is the aviso based on 10-day period and the repeat period. It's about a scale of 150 kilometers, and similar for the models. So when you go from coarse to fine, there's a significant increase in variance, as one would expect, and that get closer to the observations. But overall, and I'll show a map of the EKE in a minute, the EKE is much larger in HICOM because absolute winds are used to force the model. However, they are still significantly lower than observed, and the underestimation in the other three models is in large part due to the fact that you have relative wind, which remove the kinetic energy by as much as 30%. So there are ways to mitigate this if you look at Renaud et al. But I think the end of solution is that even further higher resolution or higher order advection schemes are needed in order to keep increasing the kinetic energy. It is, of course, more physical to take into account the vertical shear, so you have to choose a little bit between, do you want the level of EKE that is closer to the observation, or do you want actually some of the western boundary current better represented, especially in the agarose current. So here, if we look at these plots, I cannot use a pointer to show, but if you look at the pathway of the agarose current in the FSU HICOM, you see that eddies are very regular and moves into the Atlantic, so you have kind of a high energy band that's right there that is not present in the other models that use relative winds. So that's a significant improvement when using this. So, however, I mean, in order to have the right amount of eddy kinetic energy at depths, you need to also have high variability at the surface, and it is higher when you use the absolute wind, like in HICOM. But as we showed with my colleague Shabao, you need maybe to go all the way to 1/50th of a degree in order to get the level of EKE that are close to the observations. So in summary, the growth features, the bias patterns in low resolution models are significantly improved when you increase the resolution. But the main thing, and that's what we elaborate further in the full paper submitted to GMD, is that the improvement in temperature or salinity are inconsistent. So it's not because you improve the EKE as well as the pathway that the bias and TNS actually improve. And in some cases, regions show some increased bias over their low resolution counterparts. And of course, the sea surface height variability and near surface EKE are significantly improved, but still underpredict the observations. So that's it. Thank you.
Thank you, Eric. Any questions for him? Okay, we'll move on to our next speaker. We have Dujuan. Go ahead.
Hello, everyone. I'm Dujuan. Can you hear me?
Yep, we can hear you.
Okay, yeah, I'm Dujuan from Rutgers University. Well, most of today's presentation will focus on the global eddy energetics and the parameterization. My research is using high-resolution regional ocean model to examine the energetics of eddy-mean flow interactions in western boundary current systems. In particular, I will focus on the Gulf Stream and the Kuroshio Current region. Let me see how to move. Okay, yeah, mesoscale eddy everywhere in global ocean, and they are most prominent in western boundary current region. The Gulf Stream in the Northwest Atlantic Ocean and the Kuroshio Currents in the Northwest Pacific Ocean are the two most important western boundary currents with prominent eddy activity. So mesoscale eddy can exchange energy and momentum with mean currents through eddy-mean flow interaction, and therefore influence the ocean general circulation. And they can also provide important transport and mixing of physical and biogeochemical properties in both horizontal and vertical directions, and thus impact on the marine ecosystems. Ocean eddy not only affect ocean properties, they can also affect atmospheric condition above them. For example, based on a recent statistical analysis of the eddy and atmospheric conditions above in the Southern Ocean, they found warm eddies can enhance the above wind stress, cloud friction, and precipitation, while cold eddies can reduce these atmospheric features above them. Eddy can also impact the regional to Beijing scale climate. Current climate model have big prediction errors in western boundary current regions. These biases have been suggested to be resulting from the inaccurate simulation of mesoscale variability, the parameterization, and the air sea interaction on eddy scale. So a better representation of the and understanding of the eddy and the mean flow interaction will help improve the prediction of the weather and climate. So overall, a better understanding of the eddy and mean flow interaction and variability is very important to improving the prediction of weather, climate, and ecosystem in the critical western boundary currents region. So in order to study the western boundary currents region dynamic and variability, so we perform a series of 50-year high-resolution regional ocean model simulation, the ROM simulation. Our simulation domain has a horizontal resolution of 7 kilometers, and in the vertical, we have 40 terrain-following sigma layers. We have the ocean boundary forcing from SODA reanalysis dataset, and atmosphere forcing from Quora version 2 atmosphere reanalysis data. We have river runoff and 10 tidal components. Our model was also coupled with ecosystem model, which include more than 30 biogeochemical variables. We have used this kind of simulation to study the eddy and mean flow dynamics, variability, and the eddy characters. We also studied the eddy impact on biogeochemical dynamics and the coastal shelf break dynamics, as well as the impact of climate of regional ocean in the Gulf Stream region. For the analysis of Kuroshio currents, we used 22-year data from the global office simulation. So we have already published one paper on the eddy mean flow interaction in this region. We're also working on another paper on the seasonal variability and the connection of the air-sea interaction in this region. So in order to study the eddy mean flow interaction, we first derived a full set of energy equations for the mean flow and eddy respectively. So here I'm not going to discuss the detail of the derivation of the equations, Rather, I would like to use this energy exchange diagram to show what we can do using this energy analysis framework. So the active mechanical energy can be divided in, for any given ocean domain, the active mechanical energy can be divided in 4 components: mean kinetic energy, eddy kinetic energy, mean available potential energy, and eddy available potential energy. These energy components can interact with each other through instability processes. In particular, the red and blue arrows represent the EKE production due to barotropic and baroclinic instability. So here I want to highlight 2 important terms in our energy equation derivation. So we notice that the terms above the red and blue arrows actually have been widely used when people evaluating the barotropic to baroclinic conversion. In our derivation, we include 2 more terms. These terms plays an important role, play an important role in evaluating the inverse energy conversion from the eddy field to the mean currents. We will show later in our future slides. Okay, so this mechanical energy can exchange energy with the external ocean domain through energy advection. So they can also interact with external atmosphere through wind work and heat flux exchange. These energy terms provide us a way to examine the air-sea interaction on the eddy scale. If we apply this analysis to the coupled air-sea simulation, we can clearly see how the eddy mean flow interaction and also how the air-sea interaction on large scale and eddy scale play a role in affecting the ocean dynamics and the air-sea exchange. Moreover, the mechanical energy can also turn into internal energy through friction, bottom drag, and other dissipation process. Arranging all these, we have this energy analysis framework. So today I will only focus on the orange part about the eddy mean flow interaction. So we first look at the Gulf Stream region. So we have 4 study domains: the Gulf Stream domain in black, and the along coast region in pink, upon separation in blue, and off coast region in red. So we will skip this slides, go to the energy conversion, because we want to see how the eddy mean flow interact to each other. So the horizontal distribution of the energy conversion, we can see for the mean flow to eddy connected energy conversion in the along coast region, we can see clearly the cross stream variation with the mean to eddy conversion on the offshore side and the eddy to mean conversion on the inshore side. And in the off coast region, we can see complex the pattern of the mixed positive and the negative eddy to mean flow interaction. So in the vertical, overall, we can see the eddy, the energy conversion is from the mean flow to the eddy field. But in the Gulf Stream off coast region, we notice the inverse conversion from eddy to mean flow, from EKE to MKE throughout the water column, and the EPE to EKE below 200 meters. In order to get a quantitative evaluation of the eddy mean flow, we do the volume integration of the energy conversion term and get this energy budget of the Lorentz cycle. So for the Gulf Stream region in black, in general, the energy, the power is transferred from the mean flow to the eddy field. And also the EKE production is the dominant process. EKE generates through 2 pathways: the barotropic pathway from MKE to EKE, and the baroclinic pathway from MPE to EPE and then to EKE. We also notice MKE plays another role to support the baroclinic pathway besides the direct generation of MKE. For the Gulf Stream along coast and upon separation region, the energy cycle are the same as the Gulf Stream region. The only difference is their relative contribution of barotropic and baroclinic conversion is different. In the upon separation region, the barotropic conversion is much more important than baroclinic. The most important feature is for the off-coast region. We can see the energy cycle change direction. EKE change from the energy source become the energy sink to energy source. Now the EKE transferring energy back to support the acceleration of the mean flow and to increase the eddy available potential energy. I only use one slide to show the energy budget in the Kuroshio Current region because we don't have time to look into more details. In the Kuroshio Current region, we analyze the KC1, KC2, and KC3 as the Kuroshio Current region. And in this region, energy is mostly transferred from mean flow to eddy field, and EKE is the dominant. EKE production is the dominant process. And in the Kuroshio Current region, we can notice the inverse energy conversion from eddy field to the mean flow. While in the ocean interior, energy is also from the mean flow to eddy field, but the barokinetic conversion is more important than in the Kuroshio Current region. I use one slide to compare the energy cycle of Gulf Stream, Kuroshio Current, and the global ocean. We can see all these three regions have the same energy cycle. The direct energy cycle direction are the same, but the relative importance of barotropic and baroclinic conversion are different. I further compare the energy cycle of global ocean and the global atmosphere. We can look at the two figures on the right-hand side. We notice that actually in the atmosphere, MKE is energy sink and MPE is energy source. While in the global ocean, MKE is energy source and the EKE is energy sink. This indicates that atmosphere is more like a heat engine converting the thermal energy into mechanical energy, while ocean is more like a windmill that converts the wind energy into rotational energy of the ocean eddies. So I will use one more slide as a summary and outlook of this research. So we derived the energy analysis framework that can be used to study the eddy mean flow interaction, the air-sea interaction, and the eddy energy advection. We apply this energy analysis framework to the numerical simulation to study the Gulf Stream and Kuroshio Current eddy mean flow interaction. So this research actually have a lot of potential outlooks. So this can help us better understand the marine ecosystem related to the ocean eddies, and also help us to improve the weather and climate prediction if we can including the air-sea interaction component and analysis. This analysis can also provide a model-based benchmark for future observational work and numerical study in the Western Boundary Current region. Yeah, and I hope this regional high-resolution regional study can provide some details and insight for the global energetics analysis and parameterization. Yeah, thank you so much.
Thank you, Dujuan. Any questions for her? Reminder, take yourself off mute if you do, or you can type into the chat box.
Did you examine the resolution sensitivity of these energy cycles?
No, actually, I only analysis this 7 kilometer resolution simulation data. I haven't do the test of resolution.
Any other questions? All right, I think we'll move on to our final talk. It is by Sylvia Cole from Woods Hole. Okay, go ahead, Sylvia.
Thank you. I'm Sylvia Cole, and together with Kyla Drushka and Ryan Abernathy, we are leading a component of the Eddy Energy CPT that has the ambitious goal of synthesizing observations of eddy energy in the global ocean. So the goal behind this overall is to create and utilize that observational synthesis to better understand the role of eddy variability in the ocean and climate system. This is an effort which is just beginning, so I'm going to sort of outline the motivations for it, and the way we'd like to see the sort of community involvement with it, and less focus on results from that. The motivation really is partly the eddy energy CPT, but the recognition that energy is a fundamental metric of the ocean and climate system, and that mesoscale motions will store and transfer significant amounts of energy both in the ocean and how that impacts the climate system. And so we have a large need to understand eddy energy, which the talks today have basically outlined pretty well, both to understand the ocean, but also to validate models and parameterizations. The idea being that we can improve mesoscale parameterizations better if we can validate the eddy energy and the eddies directly instead of the resulting tracer fields after quantities are already stirred around. So there's sort of the two goals to both understand the ocean directly from the observations, as well as to use this routinely as a way to validate models and parameterizations that are behind this. To sort of think about synthesizing observations in the global ocean, there are a few different challenges. Observationally, the intercomparisons have not been straightforward for a number of reasons. One of the main reasons is that mesoscales occupy sort of broad spatial and temporal scales. We're talking anywhere from 10 kilometers to a few hundred kilometers, and time scales of days to sort of months. They're created and destroyed by numerous processes, and the energy estimates, because of those two things, are sensitive to the details of sampling and analysis. So different platforms will observe the eddy fields in different ways, which makes it not necessarily challenging, but you have to think about it in order to compare those observations together. In addition to this, we sort of think on a global scale, we have estimates at the surface from the figures shown here from aviso geostrophic velocities or eddy kinetic energy from surface drifters. But on a global scale, observations at depth, for the most part, do not really exist. We don't have global coverage. We have spotty coverage here and there. So we are going to actually try to bring that together and focus on the subsurface region for the CPT. When we talk about energy, this has been outlined pretty well today, but I'll simply say it again. Oh, not all of these are showing up, but at any rate, we're talking about mean kinetic energy, eddy kinetic energy, sort of mean potential energy and eddy potential energy. Think of it as 4 different reservoirs. There are also reservoirs when you start talking about, is this surface intensified or at depth, or is it geographically located and things like that. And you can transfer eddy energy between all sorts of reservoirs in that sense. From an observational standpoint, it's straightforward to calculate, provided you have a method to estimate the mean. And that's often a choice in the observations, and it can vary depending on your platform and the details of the observations. We're taking the view that all estimates of eddy energy are valuable, regardless of how you define the mean. There's a reason to try to bring them all together and do some intercomparisons and see what that tells us about the mesoscale eddy field and the eddy energy. So the sort of call for the community here is that we're encouraging on the short term to first and foremost treat any energy as a valuable metric and estimate it routinely from observations. A lot of the time, we have the observations, we can estimate it, but we're focused on something else. And if it's a straightforward thing to do, we should be routinely estimating eddy energy. We'd also like to make those eddy energy estimates available, whether that's publishing the data or at least reach out to the CPT team at a minimum and say, hey, I have this, do you need it? We're kind of looking to bring a whole bunch of different eddy estimates together. In the long term, it would be great to sort of have a long-term goal to publish those derived data products, the existing estimates, to update derived products for cases where the observations are still ongoing. And also to publish the code used to derive the data products. And that's perhaps an ambitious goal, but it's one we're going to set nevertheless and try to meet. I will say that from the standpoint of the CPT, we're sort of interested in 10 to 300 kilometer scales. But again, all estimates of eddy energy are valuable. the sort of outlook for this, this has a focus and an aim to look at the eddy energy. We can go beyond that, and obviously energy transfer between reservoirs or scales are of interest, or other things, other diagnostic metrics beyond that energy storage are useful. This includes temperature and salinity variance. So instead of validating a model to the mean salinity field, you can also see how it validates to salinity variance, which is the figure that's shown here. This is simply salinity variance at 10 meters depth and 1 degree bends from all of the Argo profiles. And so that's an additional metric to bring in to help someone validate these models that has information about some of these eddy scales and some of the mesoscale. So again, all spatial scales would benefit from this routine estimation and dissemination. Even though the CPT is focused on the mesoscale, the mesoscale estimate should be out there as well. And in particular, while we're focused on a global scale, there's a great need for a regional synthesis in a lot of different places as well. If we saw that come together, you know, because we sort of have this effort and this push, that would be great. So to quickly summarize, we're looking for a global observational synthesis of eddy energy. This is in the beginning stages. It's an ambitious but needed goal. We welcome collaboration, and I've just put up there the Eddy Energy CPT website. And first and foremost, we want to make those eddy energy estimates routinely estimated and made available. So with that, I will take questions.
Thank you, Sylvia. Any questions for her?
So Sylvia, and also maybe Stu as well. Sylvia, you focused on the spatial scales of interest, but Stu pointed out that if the seasonal cycle is blended into the definition of eddy, there can be problems. Do you have a sense of how to think about the time scales?
Yeah, so the time scale is equally important, certainly. And again, I'm going to go back to our kind of defining viewpoint that all estimates of eddy energy are useful and contain useful information that we need to figure out how to put together. And that's the time scale issue is another reason why it can be challenging to bring the observations together. Whether to include the season or cycle or not, I'm not going to tell you which way to do that, but I hope maybe we can come to some sort of sense of what that means if you do or you don't. Yeah.
Any other questions? We have, looks like we have 7 minutes. We could open it up for a general discussion as well. And I don't see any questions in the chat, and I don't see anyone speaking up. So I think we can end it right there. So thank you to the Variations and Exchanges authors for taking the time to present today, and big thanks to Simon and Baylor for helping put together this issue. We will have a posting of this presentation on the US CLIVAR YouTube channel within the next couple of weeks, so stay tuned for it. With that, thank you again, everyone, for participating in today's webinar.
Yes, thank you, everyone. It's an interesting series of meetings, talks, and papers. So, and thanks to CLIVAR and US CLIVAR for supporting us.
Yeah, likewise, thank you very much. And the webinar is a really challenging format, I think, for the speakers, because you don't get the eye contact and visual feedback and synergy with the audience directly. But in a COVID-19 world, we may be doing a lot more of this in future. So it's good practice and very nice presentations today. Thank you.